Hi everyone. So we're going to start a new module by talking about spatial relations. And really this is an extension of the data wrangling that we saw in the previous module. We're going to expand the context to look at joins through relationships in space. We're also going to continue to practice our tabular joins, our group by, but we're going to extend these to the case where data sets are related by virtue of how close they are, or whether they overlap in space. The example we're going to use is this data set of food pantries, which is put together by the Los Angeles city controller. And this is, you can use the API as we did in the first module to access it. It's also in your GitHub repository just for convenience or in case things change. And so that's how we're going to read it in. So import our display, which is alternative to print. It's better for some pandas data frames. We'll import geopandas, we'll import pandas. We'll read this data set, and let's look at the first 5 rows and the columns. So we see that we have food pantries, food banks, other food providers, and what are the columns? It looks like it gives us the address, the city, the state, and a brief description of what this resource is about. Now this is a statewide data set, but to keep things simple, let's limit to the county of Los Angeles, just to keep things fast and manageable. So this is going to return true or false, and then so the true values, that's what we're going to use to filter our rows. So we're going to store only, or keep only, the ones that are in county of Los Angeles. Now I want you to pause the video here and look at the columns and think, which columns are going to be useful to you if you want to extract the spatial information? Well, this is a regular CSV file, right? So it's not spatial inherently. But there are 2 columns that may be useful, latitude and longitude. So the trick here is how we convert these to a spatial object that GeoPandas is going to know how to interpret. Right now, there's nothing special that means these are just 2 columns that could be anything. They're just called latitude and longitude. GeoPandas doesn't recognize these automatically. So we're going to use the GPD points from XY to create the geometry from these 2 fields. Now if you look at the GeoPandas documentation, it's pretty helpful. It tells us we need an X, a Y, there's an optional Z, which usually refers to height, and an optional CRS, or Coordinate Reference System, or a projection. And even though this is optional, it's very good practice to specify what coordinates your data are in. And then there's some examples here, either some points, and also some latitude and longitude examples. So this is the X, this is the Y, and then our coordinate reference system is 4326. Most of these codes you don't need to remember. 4326 is perhaps the exception. This is a really common map projection, or it's actually not projected, it's just latitude and longitude. So if there's one you remember, it should be EPSG 4326. That just means latitude and longitude. So now let's turn our pantry data frame into a geodata frame that has spatial information. Let's call it pantry GDF. So I'm going to call our geodata frame constructor. With the data from pantry data frame, the difference is going to be, we're going to tell it what the geometry is. What's the geometry? Well, it's through these points from XY, which are the longitude and the latitude column, and then we're going to tell it what the coordinate reference system is. So let's look at the first 5 rows, and so we see we get exactly the same, but we have a geometry column. This is the only difference. So it's taken this longitude and latitude and put it in the shape of a point. You can use a CRS attribute just to double check that we got the right CRS. Yes, it's 4326, which is latitude and longitude, and it's in degrees. So now let's just take a quick look by mapping it. Now these base maps are going to, from contextually, this is what we used before, are going to be in Web Mercator by default. So we're going to need to do a transform. So we'll import our libraries, we'll create a blank figure object. So we're going to use the toCRS to convert our geodata frame to Web Mercator. If you remember 4326, that's one. The other one that's useful to remember is 3857. This is a really common standard for web mapping. And so we're going to transform our data set to this projection, and then we're going to plot it. We're going to plot the points in red color on the axis object that we just created here. Then we're going to add a base map, and we're going to remove the axis ticks and labels. Those will tell us the latitude and longitude. So we just set them to an empty list to remove them. Okay, so this is a high-level overview of where our food pantries and food banks and similar facilities are in Los Angeles County. So far, so good. Do take a look, pause the video, and see what happens if you remove the toCRS part of the code. So what happens if you remove this? What's going on? See if you can explain it. Well, let's try this ourselves. What happens if we take this out and then plot it? Well, we get our points, but no base map. Actually, if we look at the latitude and longitude, this actually tells us what's going on. So our points are being plotted in that long, which is our projection of pantry GDF. But our base map is in Web Mercator, and so there's no base map at these locations at, say, 33.8 minus 118.6. That doesn't exist in Web Mercator. We just get a blank. So that explains why we didn't get a base map, because it doesn't exist at this location in the Web Mercator projection. So if we just want to look at the locations, this map is fine, but doesn't allow us to do any analysis. For example, how do food pantry locations compare with neighborhood characteristics? So to do this, let's load in our other data sources. So let's get some census data to see how the presence of a food pantry or food bank correlates with neighborhood demographics. So we've seen this before in Module 2. We're going to use SenPy, and we're going to use the American Community Service data from 2017. We're going to get everything in Los Angeles County at the census tract level. I looked up what this variable was before, B190190001E. This is median household income at the census tract level. And then this isn't meaningful to any human being, so let's rename that column so that rather than calling it B19019 and so on, we call it median household income. And then we're doing it in place so that we're modifying income data frame rather than returning new data frame with a renamed column. And let's look at the first 5 rows. It takes a little while to get the data from the census API via SenPy. Okay, so we get a future warning. This is something that's deep in SenPy. This is really a message for the SenPy developer to worry about, that something's going to change in a future release. So we get our income data frame, so median household income for census tracts in Los Angeles County. The other data set I'd like to join is EnviroScreen, which is a great data set that focuses on environmental justice. And so we're at 4.0, and you can read about it here, including the data dictionary, which you can download from this link here if you want to know what the columns mean. This gives us data on air pollution as well as on demographics and other forms of pollutants. So this doesn't have an API. We can actually download it and load it. It's actually in your class Git repository. And so we used GPD read file before to get a URL from an API. So we passed a URL here. But here we're going to pass a file name. This is a shapefile that we're loading in from disk. And let's look at the first 5 rows of the EnviroScreen data frame. You can see here that we have census tract information, the zip code, city, various pollutants, as well as some demographic information. So first of all, let's do a tabular join. So this is similar to what we did in the last lecture. We're not going to join on the spatial information because we actually have the tract ID for both the census data and the Cal EnviroScreen. If we can avoid doing a spatial join because we have a column to join in, that's usually preferable. It's faster, it's more robust. And it looks like both data sets have this census tract, right? It's called GeoID in our census data, and it's called tract in our EnviroScreen data. Well, the census data is for Los Angeles County only. EnviroScreen data is for all of California. So let's do a left join from the census data, which we called income data frame. And that means we're going to only keep the Los Angeles County census tracts. If we do a left join, we're going to throw away all the non-LA census tracts in the rest of California. So let's set the index for both of these so that we can join on the index. Again, it's called GeoID in one and tract in the other. And we don't need to specify a left join because that's the pandas default. Okay, what's our error message? You can scroll down, read up from the bottom. Okay, we get the same errors we did before. Both of them have geometries. And we looked at how to do that in the previous lecture. So let's do that. Okay, so we join, we don't get an error this time. But here something went wrong. Like all of these EnviroScreen values are null. So what's happening? We didn't get an error message, but something is going wrong. Well, a good place to start with this is through looking at the lengths of the data frames, like the number of rows. So let's just print the length of the initial data frames and joined. So this looks fine, right? We want to do a left join, and we had 2, 3, 4, 6 census tracts in LA. We're dropping the ones that are not in LA. We have 2, 3, 4, 6. So that doesn't seem to show any problem. What about describe? Well, this is another helpful function. It gives us descriptive statistics, counts, means, percentiles, and so on. Well, here we see the problem. That we keep our household income, but we're not getting any information at all from EnviroScreen data frame. So I'd like you to pause the video and think about how you might troubleshoot this problem. What's going to be your next step? How are you going to figure out what's going wrong? Well, I thought that, well, we're joining on the indices, so let's take a look at the indices. Let's look at these join columns. So this is our income data frame index. So it's a string with the census tract zip code. Okay, so this makes more sense. Then in EnviroScreen data frame, these floats. These are numeric representations of the census tract. So Pandas doesn't know how to join a string to a number, even though if you're a human and you can just look at these, you might be able to tell what's which goes with which. And also note that these numeric versions here are missing the leading 0. So we have 06. 06 is a state FIPS code for California. It's dropped off when we convert to a numeric format. So what we can do is convert these numbers to strings. And then we can use a handy function called zfill, which adds the leading 0. So for example, if we do zfill from a string 11, that's going to keep adding zeros to the front until we get to a string of length 11. Basically, 0 pads a string representation of a number. So let's drop the index, put it back as a regular column. This is easier to apply functions in pandas to columns rather than indices. And let's create a new column, let's call it GeoID, to match the census tract data. And so we're taking what's in tract, and we're converting it to a string, and then we're padding that with a leading 0 until it's 11 digits long. So let's look at our GeoID column. Okay, so we're not exactly there, right? We don't have the leading 0 because it's already more than 11 characters long because we had this decimal point. So we're close, but not there yet. So how can we get rid of this decimal point? Well, one way is before we convert to a string, let's convert track to an integer as type int. That will drop the decimal point and the 0, then we convert it to a string, and then we pad with zeros. So let's see if this works. Okay, this looks much better. So now let's try the join again. Let's put GeoID back as our index and join it to our data frame the same way as we did before. Remember, we're dropping the column geometry because that was overlapping. Okay, and this looks much more appealing, right? It looks like we have the data from both EnviroScreen and the median incomes from the census. Let's just double check we have the right number of rows, describe the results. Yep, we have our left join, the same as we started with. We don't have census tracts being duplicated, and we have data for what looks like it's complete. Okay, that was a tabular join. Now let's go back into space. How do we join the food pantry data with this merge join data frame that we just created? Now, joining EnviroScreen with census, we could take advantage of this FIPS identifier for census tracts. The food pantry dataset, unfortunately, doesn't have any geographic identifiers like that. It actually has zip code, but it doesn't have census tract. It just has this point location. Well, the income and EnviroScreen data, our join data frame, these are at the census tract level. So let's try and identify which census tract a pantry is in. Now in GeoPandas, a spatial join is accomplished using the sJoin function. And some of the principles for tabular joins are the same. You can have inner spatial joins, you can have outer spatial joins, you can have left, right, many to one, one to many, and so on. We can see in the documentation that inner join is the default, whereas pandas, it's actually the left join. So we're joining our left data frame, our right data frame, and if we don't specify how, we get an inner join. And the default predicate is intersects. We'll talk more about that in a moment. If you're familiar with QGIS or ArcGIS spatial joins, these predicates, the terminology is going to be exactly the same. Intersects, contains, and so on. Okay, and there's some helpful examples here that you can look through yourself. So let's use our sJoin function. We're going to join data frame to our pantries. And we're going to do intersects. We actually didn't need to save that because that's the default. And let's look at what we get. Okay, we get a warning. And we actually get 0 rows in our joined column. So our join failed. Here, the GeoPandas warning is actually, it's not an error. It still lets you go through with it, but it's a warning that something may not be right. And it's very helpful. There's a CRS mismatch, so that our coordinate reference system or a projection in one data frame, so join data frame, is different from what we have in pantry data frame. We're trying to join something that's in Web Mercator 3857 to something that's in lat long 4326. And to do a spatial join, these data frames have to be in the same projection. Now, if you're measuring distances, as we'll do in the next lecture, the projection matters. You might want meters or feet rather than degrees. But when we're doing intersects like now, they just have to be the same projection. It doesn't matter what they are. So we can choose 3857 or 4326. And I'm going to reproject pantry data frame to 3857, Web Mercator, and let's do the same thing. And now it looks like we got a join. And let's do our post-join checks again. Let's look at the rows. Here we got an inner join. So we actually get fewer rows in the final result than we did in either the number of pantries or the number of census tracts. And that's not surprising, as some census tracts may not have a food pantry. We also might think that some census tracts have more than one pantry. This would be a one-to-many join. And a quick way to look at this is the group by function that we saw in the previous lecture. Rather than asking for the sum or the mean, as we did before, we can ask for the sizes of each group. So grouping by the index, a level equals 0, which we saw before, which is the GeoID, let's look at the size. So you can see that most of these census tracts are just joining to one pantry. If is that the case, let's describe. We actually see that the maximum is 3. So in one census tract at least, there are 3 food pantries. Well, what about the minimum? Well, the minimum is 1. Does that mean that every census tract has 1 pantry? Well, no, because we did an inner join. And so we told GeoPandas to throw away any census tract that didn't match with a food pantry. So the minimum is 1, not 0. We still care if a census tract has no pantry at all. So how do we get these zeros back? Well, the easiest way is to join this number of pantries. We just created this pantry count series back to our join data frame. Remember, join data frame is our EnviroScreen census data set. And if we do a left join from join data frame, we'll keep all the census tracts, even those that don't appear in this pantry counts, even those that don't have pantries. Pantry counts is indexed by GeoID, we just saw that. That was the index here. These are our FIPS codes. So is join data frame, so we can join on the index. A little quirk is we need to make sure this series needs to have a name before joining, otherwise we'll get an error. Again, pause the video, try it yourself without this line, and see what happens. Okay, so we get, for simplicity, let's give this the same name. Let's look at the length before. We had 2, 3, 4, 6. Let's look at the length after, 2, 3, 4, 6. Great, so we have a one-to-one join, and we also have a left join, so this is what we expected. We're not getting any more rows, we're not getting any fewer rows. There are 2, 3, 4, 6 census tracts in Los Angeles County. And then it looks like so if things worked, we have a pantry counts, or n pantries column on the end. Now it's null in some cases, there's 1 in this census tract. There's null in many cases because there are no pantries. We know these are zeros, so let's use fill NA. So this tells pandas that for the n pantries column, any null values, we want to fill them. What do we fill them with? We want to fill them with 0. And we want to do this in place, so we want to modify join data frame rather than returning a copy. And now we should see that in pantries we have zeros in the right column here rather than nulls. So now we can do some plots, making use of our food pantry data set and our income data. So let's do a scatter plot. For our join data frame, let's plot these 2 columns against each other. So it looks like there's some relationship, perhaps. It would be nice to add a line of best fit. To do that, we can use Seaborn. Now, Seaborn is a library that's built on Matplotlib, but in general, it's a little more advanced. It makes prettier plots and has more statistical functions. So let's import it. SNS is the convention for Seaborn. And we're going to use the Seaborn regplot function, a regression plot. What's our x variable? What's our y variable? What's our data frame? And regplot gives the line of best fit between these 2 x and y variables. And there's a confidence interval too. So it looks like there's a very shallow slope. Right? Census tracts with higher median income have fewer pantries. How do we interpret that? Well, it could be need, right? In lower income census tracts, there's more need for food banks and food pantries. Or it could also be exclusion, that wealthy neighborhoods are saying no thanks and finding ways to exclude these facilities from their neighborhoods. Which of these it is, well, we can't answer with these data. Before moving on, we can also answer this reverse question. So what are the characteristics of census tracts that don't have any pantries, that have 1 pantry? Let's go back to group by. So join data frame, let's group by the number of pantries and ask it for the mean of the tract level median income. So you can see, just eyeballing it, that census tracts with no pantries have a higher median income than those that don't. But this would be a nice bar chart. So let's use the pandas plotting. We'll create a blank axis here. This is the same line of code as we had in the previous cell. We'll just pass the results to plot. What kind of plot? We want a bar. We want to plot it on this axis object that we created here. And then we'll add the X and Y labels. This is a little more digestible than just looking at the table. In pantries, census tracts with more pantries tend to be lower income. So let's recap. We did a lot of join operations in this lecture. So I want you to pause the video and go through step by step yourself through the previous code. And each step, figure out which data sets you're joining and how you're joining them. Are you doing a left join, for example? Are you doing an outer join, for example? And on which column or spatial relationship? Well, let's recap what we did. Well, first of all, we joined our income data frame to EnviroScreen data frame, a left join using GeoID. Then we did a spatial join. So this is the join data frame we created. And so we brought in our pantries, and we did an inner join between pantries and our joined income and EnviroScreen using intersects. Now we took that one step further, and we grouped by this GeoID column to get the counts. And then finally, we joined these counts back to our joined data frame here, and we use the same name just for clarity, rather than using join df2, join df3. And we did a left join on GeoID, and then we filled the NANs with zeros. So there's a lot of steps here, but we can break it down into which data sets we're joining to which and how in this type of diagram. This is always useful to sketch out yourself if you're doing your own join operations. So as we saw before, data wrangling, it does need some trial and error. You're going to get error messages, you're going to get unexpected results, and you're going to need to use the detective work tools that we introduced, map them. Look at the counts of the number of rows. Look at your descriptive statistics using group by describe to see if the output is what you expect. Now, spatial joins use a spatial relationships rather than a common column. Intersect is in most column. For example, points will intersect with polygons if they're inside or on the boundary. But there's others that we're going to cover in the next lecture. And then finally, we briefly introduced Seaborn. It's a very similar library to Matplotlib, but has a lot more advanced functionality and in general makes some prettier plots. We'll see Seaborn a little more in the lectures to come.